Ready?
Yeah.
Let's go. If I get everybody's attention. Our ultimate speaker for the day is the ultimate speaker, Steve Miller. I'll let him continue.
I was hoping to get an introduction from the ultimate introducer who would at least read the title. I'm a Bostonian, I can't really read some of the words well, especially
Continued fraction digit averages and Maclaurin's inequalities.
Thank you. That's the one that was causing me heartaches. And so I would like to thank the organizers. Is Mel here? Okay. If you were here, I would thank him for giving me 40 minutes to speak today, and I would ask him if I could put 10 minutes in the future for CANT 2015. But since he's not here, I will just continue on and just talk slowly. Okay, so what I want to do is give a quick outline of the talk. And this is going to be very different than the talks I've given in the previous years on Cookie Monster and second-order decompositions, or more some in different sets. But there is a little bit of a relation in terms of some of the problems studied. So classical ergodic theory or number theory, whatever you want to look at, applied to continued fractions, gives us a couple of results, especially almost surely the geometric mean converges to Pynchon's constant, almost surely the arithmetic mean diverges to infinity. What I want to talk about today is some related quantities you can study, not just of course with continued fraction digits, but with any sequence of non-negative, better yet I guess positive quantities. And so I want to talk about is symmetric averages and Maclaurin's inequalities. And I probably should have been aware of these a lot earlier in my mathematical career than I was. I will assume people are as ignorant as I am, which was not necessarily a good assumption, but I'll go over a proof of these inequalities. It's a really nice generalization of the arithmetic mean, geometric mean. The hardest point was actually adjusting the text font size to get this all to fit into one line and still have it visible. So the arithmetic mean and the geometric mean sit on the extremes, and then you can just look at the kth symmetric polynomial and you normalize by the count by the number of terms you have here, and you have this beautiful descending chain of inequalities. And so of course if you look at the continued fractions, well, the geometric mean almost surely converges to a constant, the arithmetic mean almost surely diverges to infinity. Well, what happens at these intermediate values? You know, there's got to be a phase transition. Where is the phase transition? What can you say? And so the purpose of the talk is to try to answer questions along those lines. Not surprisingly, this is leading in beautifully to the problem session, which will be immediately following this, and a lot of this will actually just migrate directly with me to the problem session about things to look at. And so if anybody is interested in pursuing some of these things further, please let me know. I think these would be terrific topics, both for general research or for REUs. I know there's at least one person in the audience looking for things to bring back. The paper is currently being revised right now. It is available on the archive over here, but we've just added another co-author and are trying to massively extend some of the results. Continuing the references to people who are no longer here, I was fortunate to have two thesis advisors. One of them, who was here earlier, is a master at removing logarithms or log, stuff like that. Since he is not here, I will not be that careful, and I will leave the results a lot less sharp than they could be, but we are currently working on trying to move some of those. Okay, so every real number can be expressed as a continued fraction. And one thing that's nice about continued fractions is they are base independent. So this is not a function of we're computers and we like base 2, we're humans, we like base 10. I've got to get to 40 minutes somehow. This is a natural way of representing numbers. I will always assume my numbers are between 0 and 1, so the leading digit I'm not going to really worry about. When you're doing things such as these Maclaurin inequalities, and I'm looking at these symmetric polynomials, well, if any of my digits were 0, that would cause trouble. All those terms involving it would just immediately drop off. So we're going to assume every sequence we look at is just non-negative quantities. And so I'm going to write the following like this, or in a more compact notation, A1, A2, A3, and again, there's no A0 because my numbers are always in the interval 0, 1. So the sequence AI is finite if and only if your number is a rational number. Well, a little bit more is true. If it's a rational number, the AI's, the digits are actually just the partial quotients coming from the Euclidean algorithm. So there's a beautiful theory of continued fractions. You're finite if and only if you're rational. You're periodic if and only if you're quadratic irrational. And more generally, you're pre-periodic, so you could have some number of things in the beginning and then settle down into periodic sequence if and only if you are a quadratic irrational number. Okay, so the Gauss map, sending t of x to the fractional part of 1 over x generates the digits of the continued fraction. So here is a1, applying it to just the original element, ai plus 1 in terms of the previous. What we're doing essentially is we're splitting up the interval 0, 1, and then depending on where I fall here, this gets me my digit. I'm not going to go too much into the ergodic theory. I don't really need it, other than just knowing certain results exist in terms of the limiting behavior, but there is a lot of theory looking in the background. So the map T preserves the following measure, and it's mixing. So because I have 40 minutes, I can actually do an example. Let's take the square root of 3 minus 1, and if we've done the calculation correctly, this should be a number between 0 and 1. If not, please don't let me know. So it's 1, 2, 1, 2. The first digit is just 1. And so now I apply my map T to square root of 3 minus 1, so I get 1 over root 3 minus 1 minus the greatest integer less than or equal to this. Well, it's very simple to do the calculation. It's 1, so I get root 3 minus 1 over 2. Its first digit, its integer part is going to just be 2. I now apply the map again. Oh, it looks like it cut off. It didn't cut off on my screen. Interesting. No, that's not. And so what you then get is the next digit is 1. And so if you look at what happens is, you can see, if you have really good eyesight, there's a little bit of a red 1 over here. That's the square root of 3 minus 1. That's the number we started with. So once we apply the map twice, we return to where we have. So our sequence, 1, 2, 1, 2, 1, 2, is just going to repeat on ad infinitum. And so this is how you would calculate the digits. This is how you would do one of these quadratic irrationals. Right. So the digits AI follow the Gauss-Kreutzmann distribution. So the probability the nth digit is k is approximately 1 over k plus 2 if k is large. What's nice is that for the quantities we're looking at, when we're trying to study these symmetric polynomials evaluated the digits of the continued fraction, because these are symmetric polynomials, it doesn't matter the order in which I take the digits. All that matters is the values of the digits. So the digits of a continued fraction expansion are not independent of each other. But fortunately, we don't need to know any of those facts. We just need to know the count of each digit. And so because of that, that makes a lot of these probabilistic models to try to get a feel of what's going on far more tractable to look at than you might expect initially with continued fractions, because we don't actually care about these dependencies between digits. The function is not integrable with respect to mu, however the logarithm is, and basically if you just use some results from ergodic theory, you can get the arithmetic mean is diverging and the geometric mean is going to converge to the following integral almost surely. Or a little bit more explicitly, the geometric mean is going to converge to Khinchin's constant about 2.68. We also have the Holder means for p less than 1 almost surely. The following quantities will converge to some number. And again, interestingly, it's getting cut off on the screen here. This is, as you would expect, a 1 over p. So the harmonic means k minus 1 is about 1.745. For some of the quantities we're going to look at later, the harmonic means are actually important, because if I want to study, say, a certain product, I might want to multiply by the remaining terms that I have to complete it and have a product of all terms, and then that's the same as studying reciprocals. So a lot of the quantities, I'll pass back and forth between studying the sequence I have in its symmetric polynomial or the reciprocals fed into the symmetric polynomial. And as p tends to 0, these pth Holder means will converge to Kreutzmann's constant. Okay, so Khinchin also proved that the limit as n goes to infinity of the sum of ai up to n divided by n log n goes to 1 over log 2 in probability. So this gives you an idea of how large some of the AIs can be. So in particular, if you look at the first n digits, it is extremely likely that at least one of them will be large. And there's a whole chain of results about how many of them can be large, how large can large be. In 1986, Diamond and Valère proved that if you subtract the largest one and divide by n log n, it's, again, also 1 over log 2, almost surely.
What's almost surely mean?
Here, I think almost surely with respect to the continued fraction, the alpha that you're choosing. So for almost all alpha you choose, you will have a result like this. So again, with problems like this, I will almost surely make a mistake at some point of what almost surely is referring to. Typically, it should refer to how I'm choosing the elements alpha with respect to the big measure. Or possibly with respect to one of the other measures, but almost surely I think it's with respect to the big measure. Okay, so the Maclaurin inequalities. So, as I mentioned before, the arithmetic mean and the geometric mean, these are extremely familiar to everybody. I am embarrassed that I was not familiar with Maclaurin's inequalities as well as I should have, especially considering how many years I have supervised problem-solving teams and Putnam preparations. I should have had this, far higher in my stream of inequalities to be aware of, but at least I can remedy that now. So we define the kth symmetric polynomial, or the kth symmetric mean of x1 through xn, as I look at all possible products of distinct terms, and I divide by the number of terms I have. Frequently, it's convenient to reorder the x's to be non-decreasing, but of course, since it's a symmetric polynomial, it doesn't matter. And then Maclaurin's inequalities is just the arithmetic mean, geometric mean, sandwiched in between, and as you would expect, the equalities hold if and only if all of the elements are equal. Alright, I was told I was supposed to talk for 40 minutes. One way to do this is, well, I could go through Maclaurin's proof, but he has things like, I am, sir, your most obedient, most humble servant. And as somebody who grew up in Boston, I just can't speak like that. And so I will have to pass on his very nice prose and flowery language and go to the more standard ways, the more modern ways of proving these results. So the standard way is through Newton's inequalities. If you define ek of x to be the symmetric polynomial divided by n choose k, you have the following relation, and from this, with a little bit of algebra, you can get Maclaurin's inequalities. I want to talk about a new way that Ido Ben-Ari and Keith Conrad showed me recently, and in fact this is what got it in my mind. And then when I visited the University of Illinois Urbana-Champaign, I was talking with Francesco, and I had just been talking with Ido about these inequalities. Francesco was working on some stuff related to continued fractions, and it became natural to try to apply these inequalities and see if anything interesting could happen. Could we find a nice phase transition? So their proof goes as follows. So consider Bernoulli's inequality. So if t is greater than minus 1, 1 plus t to the n is greater than or equal to 1 plus n over t, or just changing things around, 1 plus 1 over, and x is greater than or equal to 1 plus x to the 1 over n. Well, you can generalize this to the following string. And once we have this string of inequalities, hopefully it's clear where Maclaurin's inequalities are coming from. To put into a little bit more detail, if I want to show just any two consecutive terms in the chain, this is equivalent after taking logarithms to proving 1 over k log of this is greater than or equal to 1 over k plus 1 times the log of that. Well, this just follows by log t is strictly concave, and you should never do algebra in public, but here is what you would choose for lambda and for the t's to make everything work out. Okay, so now that we have the generalized Bernoulli inequality, we can quickly prove the Maclaurin inequalities as follows. Well, if n equals 1, there's nothing to prove. If n equals 2, this is just the standard arithmetic mean, geometric mean, so we can assume n is at least 3. And what we're going to do is we'll just continue going inductively and increasing the n. So we set, as always, ek to be the symmetric polynomial divided by nk, and then e sub little k is going to just be what would happen one term before. And I'll order things, as I said, so that xn is the largest one, and just use this to decompose my stuff in a nice way. So just essentially by definition, ek is going to be 1 over k, 1 minus k over n, with just n variables, and then of course plugging in the xn over there as well. And so now you just proceed by induction the number of variables and use the generalized Bernoulli inequality, and then just do the algebraic bookkeeping. Okay. So now it's time to talk about some of the main results, which are not nearly as much of a result as I would like, and this is where I'm hoping to interest several of you to try to continue these with me, either during the problem session if we think we can do it in a few minutes, or more likely over the next few weeks. So, as always, x and k is going to be the kth symmetric mean of our sequence of x's. Our x's, for the most part, are going to be the digits of a continued fraction expansion for number in the interval 0, 1, but other sequences might be interesting and worth studying as well. And we have the following chain. So Kinchin's result, almost surely the arithmetic mean diverges, the geometric mean converges. We're going to study the intermediate means. We're going to try to find phase transitions. And so the first theorem is that if fn is little o of log n, then almost surely, so for almost all alpha that you choose, the fnth symmetric mean will diverge. And in the other direction, if fn is little o of n, then almost surely, if I move just fn steps away from the geometric mean, I'm still going to converge to Kinchin's constant. So the real question is, how far can I move away from the geometric mean and still be k naught? How far can I move away from the arithmetic mean and still diverge to infinity? Yes?
But doesn't one of these imply the other? I mean, if it's O of log n.
Well, this is n minus, so the real question right now is why the step size is different. So here I'm able to move very far away from the geometric mean. As long as I don't move a constant multiple of n away, I'm able to show that this is going to still be the Gauss-Kuzmin mean. But over here, we're moving significantly less. And this is where, if Henrik was around, I would start talking about the extension that I'm doing with some colleagues where we're replacing the log n with hopefully a little over n. And so this is far more technical, and if time permits at the end of the talk, I will discuss a little bit about what is needed to get a better step size from here than what we currently have. But the real question is, where does this phase transition occur? What we expect is going to happen is that if Fn is a constant multiple of n, so that maybe we're looking at c times n to the 1 over c times n power, then that should converge to something almost surely for all alpha, which will be a very simple function of c. And so we are far from being able to prove that. So to just give you the punchline, so if you want to go to sleep, you can do so without missing anything too important. We believe that for almost all alpha, there is a very nice answer as a function of c. But we're not able to prove that. What we can prove, pretty sure, is that there's bounds. And so there'll be very nice bounds as a function of c, and almost surely you'll be within this bounded region. Okay, so let me give you a quick sketch of the proof. So for the first one, moving a small distance away from the arithmetic mean, the main idea in the proof is using a strengthening of Maclaurin from a couple of years ago that allows me to basically replace a nice combination of two values with what's going on at two other points. And for theorem 2, moving a little bit further, the main idea is that I can sandwich these quantities between powers of the Gauss-Kuzmin mean. So because Mel was kind enough to give me a little extra time, I can actually go through some of the details. So the lemma we need is, we have a sequence of positive real numbers. Suppose this limit exists, then so long as Fn is growing slower than k of n, as n goes to infinity, if I look at what's going on at kn plus Fn, then that's essentially the same as what's going on at kn. So there's some kind of stability, some kind of continuity as you would expect. If I don't move that much, things don't really change that much. And this is just a bookkeeping argument. The proof is basically Newton's inequalities and Maclaurin's inequalities give us the following. Some of these are fairly trivial. Well, this is just canceling the k's, and so there's nothing over here. Going from here to here is almost as simple as saying, well, I have a bunch of non-negative numbers. I have a bunch of, in fact, positive numbers. So when I'm going from here to here, I'm just expanding the number of terms I have. We have to be a little bit careful because we're dividing by binomial coefficients and taking roots, but essentially I'm just adding more terms. And then over here in the limit, it's not going to really make a difference. As I let n go to infinity, k over k plus f will just converge to 1. All right, so now let's prove theorem 1 so that I can move log n steps and still get a divergent answer. And again, using more advanced techniques that I'll talk about later, we can do better than log n, but this I prefer right now because it's far more elementary. So each entry of alpha is at least 1, and it's going to be extremely important. Fn is log n, set t equals 1/2, and then just use the result, the strengthening I told you about, which is going to relate my value at n f of n to some other places. So I square both sides, raise to the power 1 over Fn. Now I use Khinchin's result. So almost surely, if g of n is little over log n, this quantity goes to infinity. And the reason goes back to what we talked about earlier for the arithmetic mean. Not only does it diverge, but we have some idea of how quickly it diverges. With probability 1, it's going to be, even if I divide by n log n, it's going to be of size 1 over log 2. So this top is going to be growing, we believe, at least as fast as log n with probability 1. So as long as I divide by something growing slower than log n, this will go off to infinity. And now when I plug things in, let gn be log n over log n, taking logs, the drowning number theorist, you get log n over 2f of n, and this gives you your growth rate. So there's unfortunately real obstructions in this method to pushing it beyond log n very elementarily. but these simple arguments do give you some idea of, you can move at least this far away from the arithmetic mean and still see divergence. All right, so now for theorem 2, how far can we move away from the geometric mean and still find convergence? All right, so now we want to show that this is still going to converge to K0. So it immediately follows from, for any constant c between 0 and 1 and almost all alpha, we have this kind of sandwiching going on. So to see this, note that, what is this quantity over here? Well, this is what I was talking about earlier, that if you have a product, what you can do is you can complete the product by putting in the terms you're missing, and then what will be left will be reciprocals. So I'm going to be left with a bunch of reciprocals over here. Well, since each number here is at least 1, the product is at least 1. So the largest this quantity could be is if I take something like the golden mean, where every continued fraction digit is a 1. The numerator is then going to just be n choose Cn, which is exactly what the denominator is. This would just be 1. In general, of course, these numbers are not all going to be 1. They'll be larger. I expect this to be smaller. And this is going to give you the sandwiching bounds. So taking everything to be 1 will get you this bound over here, because in the limit this is going to just become the Gauss-Kruseman constant to the 1/c power. For the other direction, this is just the Maclaurin inequality, that it has to be at least this large. So this gives you an idea of roughly how large things can be, and then with just a little bit of work knowing that we're not moving that far, this will then give us the result by just taking c to be a very small number that's going to tend to the appropriate quantity. Okay, so limiting behavior. So as always, here is my kth symmetric mean. My inequality is going down like this. For almost all alpha and any c between here, we end up getting a little bit better over here with the k to the -1. So this is again the harmonic means, and again it's it's playing these games of looking at these reciprocals. We conjecture that if you take any alpha, we can get these lim sups and lim infs. They'll exist, they'll be equal, and they'll be independent of alpha. Now clearly, of course, something like this can't hold and be independent of alpha for all alpha. This would be absurd. If I just take my alpha to be all 2s, all 3s, all 4s, I will get very different answers. The idea is for a generic alpha, you should get an answer that's universal and independent of alpha and only depends on c. And again, it seems quite unlikely that you would have specific values of c that would cause issues for almost all alpha. So I expect these limits to be continuous and have very nice properties. All right, so we'll define with alphas to be these limits, but we conjecture that for almost all alpha, the limit exists and is independent of alpha. If we assume our conjectures, we can show that at least this mapping is continuous. If the conjecture is false, we have some control over how bad things can be. All right, so here is just a colorful plot. My kids like it. And so just you're choosing 3 values of c, 1/4, 1/2, and 3/4, and then choosing 3 different continued fractions that are between 0 and 1, pi -3, gamma, and sine of 1. One thing that would be very interesting to look at is how the structure of the number affects the convergence and affects the behavior. For something like this, we have very little information about which set of numbers actually satisfy they converge to the Gauss-Kruseman constant K0. And so it would be very interesting to look at your cubics, quartics, quintics, transcendentals, see if you can detect anything about rates of convergence. For some talks I've given on Benford's law, there's a huge change in behavior based on how well approximable some numbers are by rationals. And it would be interesting to see what kind of impact that has here. You would expect some of it might come into, do you have abnormally large digits in your continued fraction expansion? And so things like that should probably affect what's going on here. Computationally, this was a lot harder than we initially expected, but as soon as we started thinking about what was going on, we realized we shouldn't have been surprised that this becomes a computational nightmare. If you look at how many terms you need to evaluate to calculate these kth symmetric averages, you can see how quickly the number of terms grows, and this is why, for the most part, we're only looking up to about n equals 1,000. So of course, there's always the danger of not seeing the limiting behavior from looking at small regimes, but in terms of looking at 50,000, 100,000 digits, well, it is very easy to calculate those continued fraction digits. To actually then evaluate the symmetric polynomials is a bit involved. If anybody's interested in trying to find good ways to evaluate symmetric polynomials at places like this, yes?
Yeah, I mean, there's a whole like theory of expressing your elementary symmetric functions in terms of ones that might be easier for computation, like
Right.
power sums or things like
Where we
that.
tried looking at some of those, and we still found it was computationally involved. And just for display purposes, we just looked at this. But I would be very happy to revisit this and see, if it's possible to get to, 50,000, 100,000, million digits.
What was conjecture one again that this is illustrating?
Which one is one? Okay, I think this is just that for almost all alpha and NEC between 0 and 1, the lim sup and the limit are equal, and they'll converge independent of alpha to some nice number. And we have some guesses as to what that number would be, but not proof, so I'm being a little bit vague and mysterious right now as to exactly what we think that is, because this is being recorded for posterity, or future students if there's a difference. So over here, for the plot, this is looking at 3 different choices of seeing 3 different numbers, and you're getting some sense that they are converging roughly to similar quantity. It looked like there was a question. Or yes.
Why do you replace n with cn here, but in the theorems you replace n with n minus f of n?
Oh, because in the theorems we can actually prove things for n minus f of n. And so, if we don't move too far, we can prove things. For the most part, we can't prove things if we move a multiple of n away. We can in some places for periodic continued fractions. And I'll talk a little bit about that in a few minutes. But in the general case, unfortunately, we don't have results. In some sense, we have results in the trivial regime. If you're only moving little over n steps, you're effectively still at the geometric mean. You haven't really moved. And then we believe as soon as you start moving a multiple of n, you see a different answer for each value of c. So we're looking at very easy values of c, 50%, 25%, 75%. Okay, so as promised, let's look at some very special continued fractions. So let's look at square root of 3 minus 1, 1, 2, 1, 2, 1, 2, 1, 2. This was chosen so I can do it in my head. The arithmetic mean is going to just be 3 halves. The geometric mean is just going to be square root of 2. And so this is an example where it is not going to converge to what happens almost surely. So this is a very special number. Now, of course, all quadratic irrationals will have something like this. None of them are going to have an arithmetic mean that blows up. None of them will have a geometric mean that equals the Gauss. Actually, is it known that the Gauss-Kreutzmann constant is irrational?
What?
Is a proof known that the Gauss-Kreutzmann constant is irrational? Okay. I mean, almost surely it is, but in terms of what the geometric means and stuff like that will be, I would conjecture that the...
Does anybody have the continued fraction to...
Right. And then calculate the Gauss-Kreutzmann constant, the continued fraction expansion of the Gauss-Kreutzmann constant, and then iterate that. And almost surely you should converge to the Gauss-Kreutzmann constant. Or cycle through it. Okay, so what can we say about the limit as if we move a multiple of n away? So if we consider the irrational xy, 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 we can actually do this perfectly if c equals 1/2. And then a good project, if somebody is interested, is trying to figure out which other rationals can we generalize our arguments to. This is the last talk of the day. I am holding us up from getting to the problem session, which is then holding us up from getting to the wine. And so basically looking 2 steps ahead, I don't want to go into too much details about the polynomials that we would use for something like this. I'm happy to talk about this in greater detail. The details are available on the slides that I linked to on the first page. I will just quickly go through this so we can then get to the problem session and then move on to the rest of the day's festivities. So explicitly, we actually find this limit in terms of any x and y. And so the theorem is the following. It converges to the half-Holder mean of x and y. So as n goes to infinity, it's going to the square root of x plus the square root of y over 2 squared. One case is very easy to do in your head if x equals y. I leave that as an exercise to the reader or the audience. So let's assume from now on that y is greater than x, because otherwise the calculation is very trivial. And it's really not a xy, xy, xy continued fraction. Alright, so we want to show that it's converging to the half-Holder mean. It actually is going monotonically. And the proof uses asymptotic formulas for the Legendre polynomials. And so just to standardize variables, t will be x over y. It's going to be less than 1 because I'm assuming y is greater than x. I'll let u be 1 plus t over 1 minus t, which will be greater than 1. And so if you let pk of u be the following expression, with a little bit of work, we see that what we have over here, 1 over 2k choose k, I'm only going to be looking at even places. This is going to be very similar to, I'm sorry, not very similar to, this is going to be our kth symmetric mean. And the reason is just because we have so much similarity, we only have x's and y's, and we have each one of them equally. I just want to know how many times do I choose jx's. Well, if I choose jx's, I choose k minus jy's. Everything's going to be blah, 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 blah. And so it now comes down to just an analysis of properties of Legendre polynomials. And so I don't want to go through things in complete detail. Here's just a rough sketch of what goes on. You're just playing games with sizes of the binomial coefficients, taking the roots, getting some ideas of the asymptotic expansions, and then just taking the limit. And at the end of the day, when the dust settles, or I guess the photon, since this is a slide talk and not a chalk talk, we get the Holder mean over here. And then, of course, what other polynomials can you do this to? Could you do it to c equals 2/3? Can you do it for x, y, z? So there's a lot of very natural things to try to extend these arguments to. And we have partial results for some of these. I can't remember exactly which status it is. We might have it if it's the half mean of a periodic continued fraction of length L, but there's definitely room to try to extend and push some of this stuff onward. So, okay, here it is. Okay, so maybe it's just a conjecture. So conjecture 2, for every alpha and every c in the limit, it exists and it's continuous. But we might have it if c equals 1/2, I can't remember right now. Or potentially maybe 1 over L would be the more natural thing to try here because we have L terms. And then this is the final slide of the results we have. So I'm looking at period 2 and period 3 continued fractions. So this is 1, 2, 1, 2, our old friend, 1, 10, 1, 10, 1, 100, 1, 100, 1, 2, 3, 1, 2, 3, 1, 2, 100, 1, 100, 100. And these lines are just calculating what we're getting for the kth symmetric averages as we let k go to infinity. And not surprisingly, the reason it looks like the staircase function is because we're looking at c times n, while that has to be an integer, so things are going to be flowed down. In the limit, we expect things to be converging to these solid curves. We have some rough idea of what these curves are. This is really cheating and just taking, I think, like 1,000 or 10,000 as the value of k to just approximate what these continuous curves should be. So in the remaining time, I want to talk a little bit about the extensions we're doing, which is joined with Doug from Texas A&M. And so recall theorem 1 had this horrible log factor, which should make any number theorists cringe. In a situation like this, if you're trying to prove something great about representing numbers as sums of primes, small terms like this are fine. But for something like this, this is very unnatural. And we want to remove the log n and get a much better estimate. And so we believe that we should be able to replace this with anything that's little o of n and still see divergence. And so we're close to proving the proposition unconditionally. And so what Doug's idea is that since it's the continued fraction expansion, we don't really care in which order the digits arise. We just care how many times we have a 1, how many times we have a 2, how many times we have a 3. And then playing some games about taking the numbers and rounding them to the nearest power of 2 and trying to calculate things like that. And this is enabling him to get upper and lower bounds. And the upper and lower bounds are actually sufficient if you're not moving too far away from the arithmetic mean to show this divergence. And if we're moving a decent amount away from, say, the geometric mean or the arithmetic mean, so that we're in this c times n regime where c is a non-zero constant, then while this is not enough to prove that the limit exists, it's enough, almost like the original Chebyshev arguments for counting the number of primes, to say that whatever we have, if the limit doesn't exist, it fluctuates in a very narrow band, which we can control as a nice function of c. So we're close to being able to have that result. And again, the idea is to just replace every number with either the highest or the lowest neighbor power of 2 from it, and then just keep track of how many of these numbers we have, and then just do some bookkeeping. So, thank you.